Hello. In today's discussion, we are going to cover supply side economics and do a very basic and brief introduction to, excuse me, how we size power plants, how we try to do a very economical evaluation to determine size of power plants, and then also look at some very basic cost data. So here's our outline. We're going to look at what are the issues to consider when siting a power plant. Um, it doesn't seem so obvious, but location is really essential when siting a power plant, particularly when there are people, neighbors perhaps, that don't want a power plant in their backyard. So we'll give you some items to consider when locating a new power plant. We'll talk about generating power plants as well as how to interconnect them, because a generator is all well and good, but if it doesn't interconnect to serve the load, then it doesn't actually have the ability to make money and make the project viable. We'll talk about T&D, transmission and distribution, and then we'll differentiate between the two because they are very different in terms of how they're analyzed as well as how they're constructed and their expected reliability. We'll discuss load duration curves and look at some of the variability of load, and then we'll adapt that to come up with some power plant sizing. Then we're going to get into some very basic electricity costs, and we'll look at different types of costs, fixed and variable, and then we'll use a concept of a fixed charge rate, which is essentially amortizing something over a long period of time and sort of keeping that as a fixed value. We'll discuss what's called capacity factor, which is how much a power plant is able to run. We'll look at different power plant types in terms of if it's a peaker or if it's a baseload plant. We'll discuss that. And then we'll do some screening curves to help you size some of these plants. Okay, so for a medium to a large generating plant, it isn't so easy as to buy a piece of land and start to erect a power plant. And the biggest reason why that is an issue is because you have to be within relatively close proximity to a high voltage transmission line. You don't want to run an interconnecting transmission line that you own privately and you have to pay for and maintain, and you have to run that many miles to interconnect into the high voltage transmission system, because it means a lot of cost to construct a line, but also to maintain the line. The utility owns the transmission system and they will own the point where you interconnect, but from where you interconnect back, you own that. And so you're obligated to maintain that, which can be very expensive. A lot of these generating companies, they're really good at generating electricity and making power plants work, et cetera. Where they don't always do so well is that they have to maintain high voltage transmission lines, which takes a different set of skill sets and a different set of management to be aware of what's going on. So it really makes sense if you can be as close to as practical to being a high voltage transmission system. And it doesn't even need to be very high voltage. If you can be within close proximity to a 69 kV system, your 30 to 50 megawatt project might have an easier time integrating into that project and being economically viable to do that. You also may not be able to build a power plant wherever you want. So in cities, there are many ordinances that will preclude a power plant from being constructed in many different areas. And that makes sense because if you're in a power plant, you have noise emanating at all different hours. You can't, so eliminate those noises at night. You just have to deal with the noise. And then also, if you are at a generating facility, you have lots of very expensive equipment that you have to have people walking around and making sure that the equipment is working as intended, that there are no leaks, that there's nothing that has been damaged. So you oftentimes will have to walk a facility, and having very good lighting of those facilities make it much easier for you to kind of find if there's a potential issue. And then also if there's anything in terms of people trying to cause issues at a power plant for whatever reason, if there's some sort of a criminal activity, then obviously the better lit a facility is with cameras, the less likely it is that you're going to go onto that property if you're trying to do some sort of damage. Well, that creates what's called light trespass, and light trespass is light that's emanating on one property, but it exceeds the boundaries of that property and spills over into adjacent properties. And there are all kinds of ordinances. If you were to go and go to your local super center, you'll see that the lighting at the front of the facility is quite bright. But then as you get further and further away from the facility, even if it's in the parking lot area, you'll actually see that the light gets a little lower. And by the time it hits the property line, it's supposed to be much, much smaller, usually less than 1 foot candle is typically what it is. Another thing that is really important to a generating facility, unless it's a renewable facility, for example, where you don't have that. But for most cases where you have a power plant, you need lots and lots of clean water. And so it's usually better to be located next to or with access to a municipal supply because that water has been treated, it's been cleaned, it has a bunch of different things. So it's preferential to have it from a municipal supply. But if you are a municipal supply that's from a well, it may not be sized adequately to support your particular project. And so you have to consider that maybe you need to be by a body of fresh water, and then you'll have to do some water treatment of that before you can actually start using it in your facility. You'll also always need backup power. You have to anticipate that a facility is going to experience some sort of loss of power for one reason or another. And if your generator is not running and there is no capability of backfeeding, you need to have a small distribution line that will actually be able to support your facility. You never want to go completely black because that requires additional configurations or additional pieces of equipment to make the system work. And if you have that backup power, you can still maintain some basic operations and keep your plant safe. This usually needs to be three-phase. Smaller plants don't necessarily need it, but the larger facilities certainly will need three-phase. And three-phase is not located everywhere. The further you are away from population centers, the less likely you're going to have a three-phase circuit running out there because there's just not enough demand for it. So it's not economically viable for the utility to construct that. There is a term in the industry called black start capability, and the concept of black start means that the facility is dark or black. There is no power anywhere, and you basically have to be able to get online completely by yourself. There's no offsite power, so you'll have to have some sort of on-site generation capability, oftentimes a diesel generator, but it could be a large enough load that you might need a small gas turbine. And you have batteries to get those systems up, the generator up and running. Once the generator's up and running, you better have sufficient fuel to be able to start to turn on pieces of equipment. And when you have that limited capability, starting pumps and motors and that type of stuff, that takes a lot of, it takes a lot for the system to be able to start that. Now, when you're interconnected to the regular system, there's all kinds of capacity to do that. But when you're running on a generator, your capacity is way minimized because you don't want to spend an inordinate amount of money for a generator that only runs maybe once or twice a year for a very short period of time. So those systems tend to be quite small, and then bringing things online is a process. You have to do one thing, then another, and then another. And so it takes a period of time to do that. You want to make sure that you're close to qualified staff. So you don't want to be, miles and miles and miles away for everybody has to travel hours to get to your facility to be able to maintain that. And it's plant operators, but it's plant maintenance, it's plant staff, it could be administrative support, plant managers, there's all kinds of different people. And so the further you are away from population centers, the harder it is for you to find some qualified staff. And then the last thing, which is surprisingly important, is you don't want to have a power plant that is located so remotely that you're going down lots of back roads, roads that aren't designed necessarily to move major pieces of equipment. That can be real difficulty if you have to move those large pieces of equipment. You have to replace a transformer for one reason or another, and you've got to get down this road that is very difficult for you to maneuver. And so it makes transportation of equipment very, very difficult. And some facilities, if you have large enough demands, like if you have really large transformers, those are actually located next to waterways that you can get from the ocean through a river and then maybe attach or connect with a dock to the facility because the equipment is so heavy, it's not able to go over standard roadways. So you can go over railroads, but you couldn't necessarily go over roadways without some special equipment. So it really is something to think about when you're trying to site one of these things to make sure that you can get the equipment out there easily. So the other thing to think about is what about your fuel? So if you are a traditional fossil fuel fired power plant, you for example, let's say you're using natural gas or planning to use natural gas as your source for fuel, you had darn well better be reasonably close to a decent sized gas line. And why I say that is because you can certainly extend the gas line out, but again, you're talking about a lot of cost, and the owner of the gas line may make it very difficult for you to do that. Plus, you don't want to own the land that that gas line has to traverse through. That can be very expensive. And so then you've got to get leases from people. And it makes it very, very difficult for you to actually access that. So staying relatively close to a gas line can minimize those costs. Also, for the size of land, it depends on the size of the facility that you're trying to do. So this is a pretty good figure that tells you based on the source of energy. So if it's fossil fuel or if it's renewable, approximately how many acres are required to produce 1 megawatt. And so you can see the top three, right? Coal, natural gas, and nuclear. Those have a defined fuel source, which means you have a fairly compressed fuel or fairly compressed energy source, if you will, for your fuel. So you need smaller amount of acres than the last few, which solar, wind, and hydro, which they don't have nearly the energy densities in the sun or the wind or in the water that feeds a hydroelectric facility. And so you need much, much more or many, many more acres to produce 1 megawatt. And so that should be a factor here because if you're purchasing land and you need 315 acres to produce a megawatt, or if you need 12 acres to produce a megawatt, and if land costs are really expensive, it really changes the equation. And so the example I use here is an acre in Manhattan. You're never going to build a power plant in Manhattan. It's just not economically viable. So if you wanted to do a more realistic comparison, perhaps you want to build a power plant on Long Island, which has some very expensive real estate. And if you had to purchase 1,000 acres of land in Long Island, that would be extremely expensive for your power project. Whereas if you were to build one in Aroostook County, that's an undeveloped area, you might be able to get acres of land for very, very little money. But the reason why we don't just build power plants in Aroostook County is if our previous one, if you remember, is you want to be pretty close to transmission systems, but you also want to be relatively close to the load because you actually have some high costs associated with that. And then the last bullet here is what are we willing to pay for electricity? So we in Maine have fairly high electricity rates relative to other people in the country. And so, we're paying fairly high electricity rates for that. But if we were to revolt as a consumer and say we do not want to pay these rates and we're going to look for alternatives, then perhaps that would require some of the utilities in the area to look at other ways to reduce costs. So does that mean less reliability? Does it mean less renewables? It's a difficult question. So, maybe perhaps you want to become part of a microgrid. So you're going to disconnect from the main grid and then just form a small grid in the area that you're talking about. Here is the power system in New England, and I will show you something sort of interesting over here. If you notice this part, you can see that is northern New England. And from the perspective of ISO New England, which is the transmission operator for New England, they maintain the transmission all of New England except for the part of northern New England. So this is Presque Isle. There's some population up there. But this portion of our land in New England actually isn't considered part of New England from an electrical transmissions perspective. So there is no wire that goes between ISO New England and northern New England. And so there is a separate independent system operator that manages the electrical grid in northern New England. So this is just a small part that is actually not part of New England. And you can zoom into this figure. I tried to do as high resolution as possible, but you can see that this is a rough idea, and this is an uncontrolled map. So this is readily available. You can go to Google and you can find this document, and then you can zoom in and see more of the same. In New England, we have the highest voltage, which is 345 kV. We do, and that's AC. We do have some DC lines, and this is the new DC line over here that's coming in from Quebec. But for AC lines, we have 345 kV. The highest deep voltage line that we have is, I believe it's plus minus 450 kV, and I believe it's this line here. that comes in from Canada. And that particular line, the voltage of that line runs at the highest voltage in New England I'm aware of. Once you start getting in New York, they have higher and higher voltages. But yeah, this is the transmission system, and this is whatever projects they're proposing for or through 2034. Some generation in Maine. So this kind of shows you the different types of generation that are located throughout the state of Maine. And again, most of the generation tends to be headquartered or centrally located where you actually have higher power demands. So in Bangor, Portland, Lewiston, Augusta area, you see a fair amount of generation in that area. You see some generation that is in the western part of the state because of wind farms. Those have good wind resources, and it's not too far from a transmission perspective to to put some stuff there. You also see some hydroelectric facilities. Again, those have really good resources in those areas, and the land is fairly economical. So you tend to see those bigger renewable projects where the resources available or the land is cheap. So we can compare generation and transmission based on, coming up with an idea of how far things are away. And again, the largest operating voltage that I've personally ever seen for a generator is 25,000 volts. And if you're in the Central Maine Power Territory, a lot of the area in Portland, their distribution circuits run at a higher voltage there. They're running at 35,000 volts. And so generation has to be run at a much smaller voltage for a number of reasons. It's hard to build generators with lots and lots of insulation, but you want to get your generation voltage, your 25 kV for maximum fuel, and you want to get it to very high voltages as soon as you can, because you're losing about 3.6 megawatt per mile for your generation. Again, you're running tens of thousands of amps. I've seen up to 50,000 amps of current that are coming out of these generators, and the I squared R losses are immense. Even with very low resistance, that 35,000 or 50,000 squared means you have lots and lots of energy loss. And so if you don't step your voltages up at the generating facilities very quickly, you get lots and lots of energy, lots and lots of energy losses. And so it also means you can run at higher voltages, but it costs about $2.5 million per mile of transmission. So again, trying to minimize those costs by locating as close to as practical those facilities, and then you get some, you get some stuff there, you get some benefits there. And you can even look here, this is showing Manhattan, and you can see there is some generation here. It's all old generation, but very small generation. And they do actually have some generation there, but you also see the transmission lines coming in and going from there. So we have generation, we have transmission, and then we have the last one, which is distribution, which is that intermediary point. So our generation generates usually hundreds of megawatts at a fairly low voltage. It's stepped up to perhaps the transmission level, or usually the transmission level, because several hundred megawatts, that's, unless you're in a really high demand area, there's not going to be a lot of need for that much power. So you distribute that, or you transmit that over farther lengths, and then you jump off, and then you have distribution points where you can distribute it to the actual customers. So the comparison of transmission and distribution, transmission again tends to be higher voltages. Usually the rule of thumb is around 138 kV. They can run longer distances because at 138 kV, hundreds of megawatts of power has a very small current. If you recall from our discussion with AC/DC circuits, we have transformers that will take the voltage higher, but then take the current down for the same level of power. So you can run much longer lines with much shorter wires with higher voltages. And you can see we've got some lattice structures here on the top right for our transmission. Once we get into distribution, we tend to run more wood poles, more monopoles, and you can have the spacing there. And so you can see some different designs. You have a monopole with all of the conductors that are on the same size. You can also have, to the right where you can see the figures, you can see either a single phase pole with a cross arm. You can see two phase with the same cross arm, or you can see three phase. Sometimes they're on the same cross arm. In this case, they're actually set up sort of in this V configuration, if you will. And the purpose for that is to kind of make it so that the lines all have approximately the same impedance. It has to do with some physical spacing, which impacts those. And that's not for the scope of this course, but that's something that you'll see to maintain spacing. Our distribution level tends to be 2400 to 35 kV. That's the highest one I've personally seen is 35,000 volts. Mostly if you're in Versant territory, it's around 1247 kV is their typical values. And then the distribution lines have lots and lots of interconnects. So your house is fed from a transformer that's usually on a pole. It could be on the ground, but it's usually on the pole. And there's a tap off of the distribution circuit to feed that transformer. So as a result, distribution circuits are a lot less reliable because they have so many interconnections going to them, where transmission systems have way less because you're trying to limit the amount of interconnections, which is reducing the reliability of the system. So it's not unheard of to have thousands or tens of thousands of interconnections on a distribution circuit, but on a transmission circuit, you might have 10 to 20 or something like that. And interestingly enough, in Versant territory, there's a 46 kV, they call it the sub-transmission circuit. So it's a much higher voltage than Versant would typically use, but it does a pretty good job of moving higher powers around the Bangor area and then making the system more efficient, and then they drop down there. So there's sort of this intermediate step between the transmission and distribution called sub-transmission. Here are some designs showing the sort of soup to nuts, if you will, for a facility. So you start to the left of the top figure, and you can see you have a generating station, typically 13.8 kV to 24 kV. If it's a smaller generator, maybe 5 megawatts or so. You might even have 4160, but most of the generators tend to be 13.8 kV and above. And then you immediately step that up because you've got very large conductors that are conveying that power out of the generator. Like I said, I've seen as high as almost 50,000 amps of current coming out of the generator. And 50,000 amps times any resistance at all, or I squared R, is going to give you a fair amount of power loss. And so you run that as quickly as you can for a transformer to step the voltage up to whatever typical voltage that you would see in your area. So these are transmission systems from 765 all the way to 138. As I mentioned, we only run up to 345 in the state of Maine and all of New England. You start going to New York and they have higher voltages. In Virginia, they go much higher voltages all the way up to 765. Now you have everything that's transmitted at those levels, but you can't do anything with it because that voltage is so high. There isn't equipment made to be able to operate at that value, at those voltage levels without having some sort of a problem in terms of, being able to manage those voltages effectively. So you get closer to where the load pockets are, and then you step the voltage down to a much more manageable level. So you would step it down to sub-transmission. Like I said, Versant's 46 kV, CMP does some 35 kV, but that's the typical one. And then you do one further step to step it down to the distribution level. That's where you typically would feed your customers. Most customers are fed from either medium voltage 4160 all the way up to 35 kV. And at that point, the voltages drop down to, with a transformer, either a pad mount transformer or an overhead transformer, to give you the 120 or 600 volts. Going into your house, you typically have 240. But if you would go to like a Walmart supercenter, they would have inside their building, they would run most likely at 480. And then you can also do things with DC, and we just put this here for DC because you can transmit DC. You don't see a lot of distribution circuits. You almost exclusively see them at transmission level, but you can just see some of the process. On both ends of the system, it's AC, but the intermediate is all done with DC. And there's some huge advantages to that. There's some downsides, but you see DC. And the reason why we have we have a new line that runs in Maine is because Hydro-Quebec wants to run asynchronously. They don't want to be locked in at the same frequency and phase shift that we are at in New England. And so they require DC links there. So there's 3 parts to a power system. There's load, generation, and transmission distribution. Load is why we exist. The reason why the bills are paid is because the consumers require load to do, or require power to do something. That's classified as load. The generation has to create all the load plus the losses in the system. And so it has to be maintained for that level. And then the T&D is basically the roadway that gets the power from point A to point B. And why that's so important is because electricity in and of itself cannot be effectively stored. So we have capacitors that can definitely store electricity, if you will, or at least electrons and whatnot. But all the other sources that we have do not store electricity. So a battery, you think that's a storage for electricity, but remember, it is a chemical storage device. It is the electrons are moved around and it's stored in the acids or the plates, and then that's how they can store energy. Same thing if you're using inertia, a mechanical system. If you have a system that is being rotated, that is inertia. So you've got some energy stored, but it's mechanical energy at that point. So because we can't really store that energy, our generation has to be matching what our load is, again, plus whatever losses our system experiences. So what are the sizes of loads? Your house might be on average, the typical rule of thumb for a house is it's about a kilowatt of load. But as I mentioned, if you're a decent sized Walmart, you're pushing almost 5 megawatts of load. If you're an industrial facility, really the sky's the limit. It depends on what you're producing and how many you're producing. It can get quite big. But because we have so many different loads, like I said, your house has 1 kilowatt standard load demand, and maybe there's 10,000 houses in your city, then that's 10,000 1 kilowatt loads. That would be very difficult to analyze by system. So we would aggregate those loads by neighborhood or even by town, depending on the level of analysis you're trying to do. So instead of calling it, Orono Barrows, for example, as a building, they might call it Orono Town of, and they would group that as one major load component there. And the load is cyclical. It changes on time of day. It also changes weekly, and it changes in the season. And the weather has a huge impact on what the demand is. So if it's a bright sunny day and it's a nice temperature, nobody may need to run their air conditioning. It might be a very low load demand. But if it's an extremely hot day or an extremely cold day, you could have real serious demands on the load. And so that variation really depends on the weather, which means it's location dependent. So if you're experiencing weather in Massachusetts, it might be a very different scenario than experiencing weather in Maine, for example. And so we can do what's called a power flow analysis to analyze how the power flows through our system, through our transmission and distribution system. And it's an actual system or analysis that's done all the time. So if you were to go to ISO New England headquarters, which is in Western Massachusetts, you would actually see that they're constantly running these power flow analysis to make sure that the system is stable and can tolerate some basic losses in the system and still maintain on the line. And so we already talked about power flowing in has to match the total of the power flowing out plus whatever losses in the system, because we are not storing any energy on our transmission system. We're losing it, but we're not transmitting it. And load has gotten way more complicated because it used to be, during the day, everybody would wake up and they turn on their coffee pots and turn on their stove and start making breakfast and start moving around. And so the load would start to pick up during the day. And then it would start to drop off at night because as people are getting home and getting ready to go to bed, they start to turn off their lights and they don't need as much load. So there was a kind of a standard way to look at things. But now, what we're seeing is in the morning, there's a fairly high level of load, but then it starts to drop. And it's not because the load has gone away. It's just that now the sun is up and the solar arrays that are on people's homes are actually taking and supporting or supplying a big chunk of what used to be demanded. And so there's this whole discussion on what are called duck curves. And the reason why they call it a duck curve is because it's the shape of a duck. Is you wake up in the morning, the load starts to jump up and then it starts to break down. And then as everybody gets home at night, the load goes up and then it really goes up as the sun starts to set because all that solar goes. And then you have a dramatic drop off when, a fair amount of people go to bed. So if you really want to look at some interesting stuff, you can look at a discussion on duck curves and see what that is. Here is showing you some variability, and this is June 2025. This is over the course of the month. So all the way to the left is the 1st of June, and all the way to the right is the 30th of June. And you can see why it's difficult to, size generating facilities, because look how much variance we have. When the peak is almost 2,100 megawatts and the minimum is maybe 800 megawatts. And so your system has to be designed to be able to supply, at least in the state of Maine, almost 2,100 megawatts. But it also has to be able to go all the way down to about 800 megawatts, and it has to be able to do that very efficiently. So this is the course of a month in Maine. This is the course of a week. Kind of looking at a peak one, and you can see over here, we drop down to just under 900 megawatts, but then we spike up to about 2,100 megawatts. And then over the course of one day, so June 24th, you can see that the load there never dipped below about 1,200 megawatts. And then it peaked up to, again, almost 2,100 megawatts of load. So this variability, even over the course of a day, is huge. You're doing almost 1,000 megawatts of difference, which is a 50% increase. And as a result, your system has to go through some pretty significant changes to be able to support the system. And so most of our electrical systems are way over designed for the average load, because we have to be able to handle a peak load scenario as shown here. So how do we use that information? Well, we have all this up, down, and we have some variability. So let's try to make sense of it, and let's build what's called a load duration curve. So what we're going to do over the course of 1 year is we're going to take all those loads and sort of average them at 1 hour intervals. And then we're going to sort them from the highest demand all the way to the lowest demand. And that's going to allow us to build this curve and help us size the generation facilities based on that. So you can see at basically 1 hour a year, I'm going to need about 6,000 megawatts. And at the end, which is, 8762, right at the end, that means the minimum that I'm going to demand for this particular location is just over 2,000 megawatts. So at a minimum for the entire year, I needed 2,000 megawatts. But for 1 hour of the previous year, I needed 6,000 megawatts. So this tells us how much load is going, how long that load is going to exist for. So if you can see 5,000 megawatts, we need about 5,000 megawatts of demand or supply for about 1,000 hours of the year. So that's how you can interpret these curves. And we're going to expand upon these again to size our power plants. This is from California and just gives you a sense of, what makes up the load. And you get a big other group, which is hard to quantify, but you can see the variability. You can see residential lighting, commercial air conditioning, residential air conditioning, and for whatever reason, the black isn't necessarily shown. And then you can look at that with time of day. So you can see that before 6 p.m. in the morning, you didn't have very much load because people are asleep. And then as you start going on in the course of the day, they'll start increasing. And look at the massive increases for commercial lighting and air conditioning around 9 a.m. when everybody's at work. And that's when the demands happen there. And then as we start to go on the other end, so we start getting to 6 p.m. or so, or something like that, then we can start to see that we have more home loads and more requirements there. Also, the lighting becomes more of an issue for residential lighting at night when people are home and it's dark out and you need that. So again, just the type of loads can have some big impact. And residential lighting load looks very different than commercial air conditioning loads. Motors and how they operate use slightly different. It's still the same power, but they have a power factor associated with it. So there's some additional things to consider when you look at air conditioning. So here again is how we build a load duration curve. So we're just kind of ordering them by the hour for the number of the year, number of the year. So you start on January 1st at midnight. That's hour number 1. And then you go all the way to December 31st at 11 p.m. And that is how you end up with these averages over time. And now we're going to reorder them. So we're no longer doing the x-axis by the hour in the year, but now we're arranging from how many hours. So that title says hour number of the year. It really should say, see if I can correct this, type this. This really should say number of hours required, something like that. And that basically tells us, okay, for 1 hour, we're going to need this peak load. For 2 hours, we're going to need this, at least this amount of load. and all the way so that for 8,762 hours of year, we're going to need this much load. So that is the entire amount of time that we have there. So here's our curve smoothed out again, and you can see where we have some information. So our max demand is 6,000 megawatts. Our lowest demand is about 2,000 megawatts. The demand is 500 megawatts or over for about 1,000 hours a year. And the demand for 3,000 megawatts is at least going to be for 7,000 hours per year. And so we'll use those to help us design and fabricate or specify the size of a generating facility. But before we can actually pick the sizes of the power plants, we have to look at things in terms of what are the factors that we need to consider. And if we just break them down into costs, we have fixed costs and we have variable costs. The fixed costs are, I have to construct the plant, which means I'm borrowing money to build the plant. And I've got to pay that money back every month or whatever you negotiate. I also have some basic staff costs, maintaining the plant, property taxes, all those different things. Those are part of my fixed costs. The variable costs are, and hopefully this makes sense, but you only have a variable cost associated with, well, your fuel is a variable cost because if you run or you don't run, you're paying for fuel or you're not paying for fuel. So that is entirely dependent on your operation. Also, if you're running at higher levels, you might need to bring in more staff. And so that would be a variable cost as well, which is we need more folks to be working to maintain our power plant output. But once you build a plant, now it's already built, you're paying a fixed amount every year. So your only decision about whether to run the plant or not is are you able to make up the difference of the variable costs? If the variable costs are so high that it doesn't make sense, you might not necessarily run. So we'll take a look at how we can sort of break those down. So our cost of capital, which is what we're going to pay for the capital to build a plant, we take our construction cost and then we divide that by our plant capacity. That's $1 per kilowatt. And we're doing it based on sort of a normalized value of kilowatt. We're not basing it on it's a 10 megawatt plant or a 100 megawatt plant. We're just basing it on a per kilowatt basis. And then that tells us what our capital cost is per kilowatt. And then we can go ahead and annualize that, and we can keep that annualized rate for the duration of the plant. We're going to assume that our loan is going to last forever, whatever our taxes are on the property, whatever the investors expect for a return on lending us the money, then that has to include all those costs. So that's just noted the fixed charge rate. And that again is just a constant multiplier based on, excuse me, the capital costs. And you can see that my fixed charge rate has a unit of 1 over year because what we're trying to do is figure out a fixed cost is $1 per nameplate kilowatt rating and per year. So that's what we have to pay every year for whatever kilowatt rating we have of our unit. Now we're going to add in our variable costs and we're going to annualize these again so we can add them together and figure out, what it's going to cost per year to run. So we're going to take whatever the cost is of our fuel, oftentimes going to be done in BTUs, but doesn't have to be. It typically is, but it doesn't have to be. So that's in dollars per BTU. We have our heat rate, which is another term for efficiency, which is how efficient our plant is in converting BTUs to kilowatt hours. And that basically tells us how much it costs us for the fuel to produce a kilowatt. And then we add in our O&M costs, which again are staff and maintenance and all that different type of stuff. So that's $1 per kilowatt hour basis. And then we multiply that by hours per year of when the plant is running. And then we have our variable costs. And this would be if the plant is running full out. We'll see how we can modify that if the plant is not running full out. So let's take a look at an example. We have a 16 megawatt coal plant. It costs $4 billion. We're going to have a 10% fixed charge rate. It's able to produce 12.8 million megawatt hours per year. Its assumed heat rate, again, is the efficiency, is it takes about 10,000 BTU to produce 1 kilowatt hour. The cost for fuel for coal is about $1.5 per MMBTU. And if that hasn't been thoroughly discussed, MMBTU is kind of an old term, but it still applies. M here is the 1 times 10 to the 3 multiplier. So it's 1 times 10 to the 3 times 1 times 10 to the 3, or 1 million. It would be better to call it mega, 1 mega BTU. That way you'd only have 1 M. But this is the Roman numeral M, so 1,000, as opposed to the mega multiplier that engineers are typically used to. So it's a little bit confusing, but this is 1,000 BTU is what the MM stands for. We have variable O&M costs of $4.3 per megawatt hour. So we want to figure out what is the annual cost per kilowatt hour. This is what we need to charge to essentially meet all our obligations. If we can go over, if we could charge more than this, then we have additional profits. If we charge less than this, then something is not getting paid. It could be the investors, it could be taxes. We don't necessarily know. So the first thing we do is we figure out how many dollars per kilowatt it takes to build the plant. So it's 2.5K dollars per kilowatt. Then we're going to analyze that, right? Because it costs 4 billion, but it doesn't cost 4 billion every year. It only costs us 4 billion at inception. So where a fixed charge rate converts that one-time charge into an annual charge. And so it costs about $250 per kilowatt a year. Go ahead and pay back for our fixed costs. Now we're going to add in our variable operating costs. So the fuel is $1.5 per MMBTU. Our heat rate is 10,000 BTU per kilowatt hour. And then this MMBTU, that's just a conversion to just show that MMBTU is the same thing as 10 to the 6 BTU. So it's just a way of making it so that you can actually see what the BTU comparisons are. And then we add in our dollars or our cents per kilowatt hour for construction or for production. And we can see that our variable operating cost is just under 2 cents per kilowatt hour. Now we're going to go ahead and figure out that this power plant is running full out, meaning it's producing 1,600 megawatts, and it's producing 1,600 megawatts for about 8,000 hours per year. So when we multiply out what it's fully producing, then we add and we determine that it's $154.4 per kilowatt year. So our annualized cost, what we need to charge per kilowatt hour to break even and again pay off the investors and the loans, is we need about 5.1 cents per kilowatt hour to make this project make sense. Now, that number would be a little bit high, depending on what our local marginal price would be for the area that we're in, but it's in the ballpark. It's reasonably close to what you would typically charge. So this plant almost makes feasible sense. Maybe you could cut some corners here and get your costs a little bit lower so that you can make it more viable. But this is a coal plant, so the likelihood of a coal plant being built in New England is pretty much nil. So you'd have to figure out a completely different fuel source. So now we're going to figure out, all right, well, now we have some costs associated with how much it takes to do this. Now let's go ahead and figure out how we can size power plants based on what their variable costs are, what their fixed costs are, and then we can figure out what is the least cost way to supply the money that we need. And so this slope here, this curve, is broken down. The first thing you have is you have the fixed costs, which take the curve all the way up to starting at 250. So if this plant never runs, I still need $250 per kilowatt year to basically pay off the fixed charge rate. And then if you look below that, you see that for the variable costs, well, if I'm not producing any electricity, I don't have any cost because I'm not buying any fuel. So that's zero. But then it works up at a slope of about 5.1 cents per kilowatt hour. And where those intersect is sort of that ideal point of, all right, this is the fixed as well as the variable cost, and those two are intersecting at 8,000 hours. And so that's where you've got that value. So then that additional slope that you see, the 1.93 cents per kilowatt hour, is what would be the variable cost that adding in the fuel there. So the last thing we'll talk about when before we're actually able to do the screening curves is to discuss what our capacity factor is. And this is just a definition. Capacity factor is if you have a 1 megawatt plant that you ran full out for the year. So if you produce 8,762 um, times 24 megawatt hours, you would have a capacity factor of 100. But for our coal plant example, we produced 12.8 million megawatt hours in 1 year. But the actual plant rating is 1,600 megawatts. And if you ran that for 8,760, so the number of hours in a year, that's the amount you could produce, but we're only running it at 12.8. So our capacity factor, meaning how much of our full capacity rating operating over the course of a year, what do we get? We get 0.91, which is extremely high for most generating facilities. We're going to take a look here at our next slide, and we're going to see the variability of capacity factors. And so you'll see nuclear is at the top, 0.9, but very little variance in the operating capacity factors. That's because nuclear power plants like to run full out, at least the ones in the US, they don't like to have any variability. The other ones start to vary. So you can see a combined cycle gas turbine, the CCGT in the on the x-axis. You can see that that's about 0.7 because it's a fairly efficient plant, but it doesn't make sense to run that plant necessarily all the time. But there are some cases when you might. So you can see the capacity factor there gets to almost 0.95. And then we start to look at some renewables. Well, so renewables, if you design a 1 megawatt PV array, 2/3 of the day, that plant isn't producing any power because there isn't any sun. So if you look at solar PV, you're talking capacity factors, 0.2, 0.25, very, very low capacity factors because you have a lot of capacity, but because the sun's not shining, you don't have a lot of ability to do that. Then you look at wind. So wind has a higher capacity factor than solar, and a lot of that has to do with the fact that the wind blows during the day, it blows in the evening. It doesn't have any impact whether the sun is shining or not. So just by that fact alone, its capacity factor is going to be higher. Geothermal is quite high because you have a fuel source, right? You have the Earth's crust, which is at a really, it has a high level of heat, and so you can actually go ahead and get pretty high capacity factors there. Tidal and wave tend to be pretty low. Hydro tends to be reasonable, but again, when you're in the spring, or I shouldn't say spring, in the spring when you have very high water availability, you get very high capacity factors, but at the end of a dry season, there might be hardly any water in the reservoir, and so your generating facility may not be operating. So where you have those non-dispatchable technologies, part of the reason is just because of the resource that you have. You can't guarantee it's going to be available. So now that we have capacity factors, we're actually able to design different types of plants or specify different types of plants. And we talk about three major different types. And it has to go based on the complexity of the plant. So baseload plants are extremely well designed and built. They take a lot of time and money to design them and to construct them because you're trying to eke every bit of energy out of the fuel that you have there. So these are highly, highly, highly efficient plants. They're literally spending a lot of time with superheater designs and reheat cycles and better feed water pumps and all these different things to maximize the efficiency of the system. So because they're built with a lot of design involved, they're very, very, very expensive to run. I mean, to build. But to run them is not necessarily that expensive because you need less fuel to produce the amount of energy as opposed to an intermediate plant, which has a pretty efficient process, not the most efficient, but a pretty efficient process. But it's more of a cookie cutter design. So you have a standard, like Westinghouse or GE or Rolls-Royce will make gas turbines with generators, and then they'll sell you almost like a package, and then you put the systems around it to make it work. Because in a intermediate plant, it's usually what's called the combined cycle. You combine the steam cycle as well as the gas cycle to make it more efficient. And so the gas plant would be run, and that has its certain level of efficiency. And then the steam plant is extracting that heat that would be wasted out the stack but it's actually used to reheat and reheats water, and then you can get some steam. So that would be an intermediate plant. So it has a fair amount of initial cost, but not as significant as, trying to do everything you can to eke out every BTU out of the system. But its fuel tends to be not as cheap or as an effective source, and its efficiency is not as high. And so an example is a combined cycle natural gas plant. Those are popped up all over the place, very easy to build, very modular, work extremely well. And then the lower one is just peaking plants. These are literally like generators that you can buy in the back of a semi. It all comes equipped with what you need. You roll it out on the back of a semi to where the load is, and then you connect the gas line to it or a fuel line, and you can create power. So these are modular. They are not designed necessarily for maximum efficiency. But a lot of times they're designed for maximum flexibility where you can locate them and very cheap to install. So these would be designed for just let's get them there as cheaply as possible. So base plants cost the most to make, but they're very efficient, so they have lower operating costs. Intermediate plants have a medium expense to build and a medium expense to cost because again, you're not trying to eke out every bit of efficiency. And then lastly, peaking plants are designed to, we just get a lot of load and we can't really support it unless we run these. So we're not worried about heat rate and efficiency. All we're worried about is these plants only need to run a few days a year. So let's get them out there as cheaply as possible. But when they run, they are extremely expensive. And you can see the different figures. You hopefully can tell by those images. You can kind of get a sense of sort of the effort involved in constructing the different facilities. And interestingly enough, the middle figure for the intermediate plants, that is the main Independence Station in BZ, Maine. So for those of you who are close to campus, you can actually drive maybe 5 to 7 miles away from campus, and you can actually look out at this particular facility. So when do you use the plant? Well, your baseload plants, they should be running almost full out the entire time because again, they're highly efficient. So whatever fuel they're getting, it makes sense to just keep them running at full output because they're not wasting any of that fuel. They're using as much fuel as possible. The intermediate plants are sort of picking up the slack where the load is, but not necessarily running at full out because again, they're not super duper efficient. And then those peaking plants, they're hardly running at all. They're just making up the case where it's overloading the intermediate as well as the baseload plants, and it's just picking up that small amount of load. And so you sort of have to determine when do you have your peak plants, when do you have your intermediate plants, and when do you have your baseload plants. So we'll take a look at that, and then we'll do what are called look at our screening curves, and we'll try to figure out like what is the decision about sizes and all that stuff. So here are the 3 different types of plants, and it goes from coal to combined cycle to combustion turbine, baseload to intermediate to peaker. And you can see what our fixed rates are. You can see the coal plant has the highest fixed charge rate, 224. Combined cycle is down to 96, and the simple or single cycle gas turbine is 64. So more expensive for coal, least expensive is the simple cycle gas turbine. Then we go to our variable costs, and this is essentially the biggest one is fuel. And you can see our variable cost for the coal plant, it's only 1.9 cents per kilowatt hour. Our combined cycle is about double that at 3.84. And then our combustion turbine is about 4.5 to 5 times what our coal plant is at 5.8 cents per kilowatt hour. So you can see that running this plant, the coal plant, for the longest period of time, it actually gets cheaper because the slope of the line, if you recall when we were looking at slope, its slope is way less steep. It starts out at a higher cost, but its slope is way less. Then we go to combined cycle, where again, it doesn't start out as high as a cost, but its slope is steeper. So at some point, if its time is long enough, these two are going to intersect, and it's going to be cheaper to run the coal plant. And similarly, we do that with the combustion turbine, which has a very low upfront cost, but its slope is so high that at some point, it's going to be more expensive to run that than the combined cycle plant. So we'll actually plot those on some graphs to see if we can compare what those crossover points are. So everybody starts off with our fixed charge rate or our fixed costs, and you can see the coal again is the highest at 224. The combined cycle is next at around 96. And then finally, the simple cycle gas turbine is around 65 or so dollars per kilowatt. And now we start running the plants. And the running of the plants means we're just running these plants full out for however much time is shown. And you're starting to see the slopes of the line have some impact. So the coal plant, you can see if it's only going to be running for, 1 to maybe 4,000 hours, it's more expensive than running that because of the initial cost than it is the combustion turbine. So combined cycle combustion turbine, I should say. So we're not going to run that coal plant for very little amount of time because it doesn't make economic sense. Where we start to see a huge difference is right over, let me see if it was annotating, it's not yet, right here. So you can see at that last crossover point, it's actually cheaper to run the coal plant than any of the other plants. So when I'm picking the size of my coal plant, this is the amount of load that I'm going to size it for. Well, this is revenue required, but I can go ahead and extend that to the load. So that's my peaking, or my base load plant. And then for my peaking plant, I'm looking for my next crossover, and I'm not doing combined cycle and coal and steam or combustion cycle. I'm looking at the next two, which is someplace around here. So you can see running my combined cycle plant is cheaper than running my simple cycle gas turbine for operating the plant full out at greater than around 1,675 hours. And so my peaking plant or my intermediate plant is going to be sized to pick up the load difference between what my base load plant is and what my intermediate point is here. And then my peaking plant, because it's the cheapest to run it for less than about 1,675 hours, it's going to be sized based on that value there, whatever it needs to make up that difference. And so that's how we can kind of come up with when do we do base load, when do we do simple cycle, when do we do combined cycle, and kind of sizing some of these plants. So this is taking that same chart we just looked at, and now we're adding the load duration curve on it. So we can take those intersecting points and then we can extend them down to the load duration curve. And then hopefully what you see is my base load plant has to be sized for 3,500 megawatts. So that's where I want to run it most of the time. So I'm going to run it at 3,500 megawatts. There are going to be some times, as you can see, where it gets above 65, where I'm not going to be running it 100% of the time, but that's okay. It's still cheaper to run it than any of the other plants. My combined cycle plant is going to have to make up the difference between here and here. So I need about 1,200 megawatts. And then it's cheaper to run my gas turbine, my simple cycle gas turbine, for less than 1,675. So it has to make up the difference between here and here. So this is where I get the best mix of affordability, peaking plants, and trying to make sure that my costs are, sort of relatively minimized. But it really is dependent on where these curves intersect. That is how you can tell how to size your plants. So those intersection points for the costs will tell you the number of hours of operation, and then you go to your load duration curve, and then you actually have the specific values of where you can size your power plants. And then if I wanted to, I can also calculate capacity factors, which is, again, what percentage, if you will, of the facility is operating at full out. So my gas turbine is very expensive to run, so I hardly run it at all. I only run it for very short periods of time because that's when it makes most economic sense. So its capacity factor is 0.1. My combined cycle gas turbine, now I'm running that a lot more. So I'm running that at about 0.47 for my capacity factor. And then my coal plant is running almost full out for the year until it gets above that 3,500. And then at that point, I don't have enough load. But at that point, I'm running it at, I'm running it most of the year at 100%. So its capacity factor is very, very high. So part of the reason your capacity factors are very high is because, like we talked about nuclear, so commercial nuclear reactors in the US, they are not designed to go up and down in power, so they like to stay at 100%. But it's also extremely cheap to run a nuclear power plant where you're running it at base load. It gets cheaper and cheaper and cheaper relative to the other technologies when you run it at 100%. Same thing with these big coal plants or anything like that. My gas turbines tend to have a lower capacity factor because they're not as cost effective to run over long periods of time as some of these more efficiently designed plants, but they're easy to build, they're quick to build, and you go from there. And then my peakers are only for those very short intervals where I have very, very high load that my intermediate plants and my peaker plant and my baseload plants can't support. So I'm running those for very short periods of time. But I don't want to invest a lot of money in those because I hardly run them at all. So that's why I can buy a simple cycle gas turbine on the back of a semi or back of a track on a trailer, and I can move it in and connect it to load very effectively. So again, this kind of goes and shows you how you got your capacity factor. So this run full load at 7,971 hours per year. This is more the exact calculations. And again, you can see our fixed cost, 224. Our average cost, this is if you just take the fixed cost and the variable costs and you average those out. And then our variable costs here, this is just adding it on to the fixed cost. This would be starting at 0. And then we add on here, and then where it intersects is at about 7,971 hours. And that tells me for this particular power plant with a capacity factor of 0.91, I need to basically make about $375 per kilowatt year, to make this project effective. This is for the combined cycle. So again, it's the exact same concept of before, but now I'm intersecting at a lower power value. I mean, a lower number of hours, and my capacity factor is much, much lower. So now I have to charge $250 per kilowatt per year to make this make sense. And I recognize that this number 375 is greater than the 254, but remember, this 254 is only running, let's go all the way back here. It's only running for, this amount of time here. The rest of the time it's shut down. So there are no operating costs with it. So I don't need to make money at that point. I still need to have my fixed charge rate. So my fixed costs all have to be eaten up or profited based on operating in this time frame. So the difference between the cost here, 375 and 254, is because one is operating for a lot more longer period of time, and I just need more energy to make that work. And then lastly, this is my simple cycle gas turbine. If you're not sure, and if you want to learn more about combined cycle and simple cycles, combined cycle is a Rankine and a Brayton cycle. So again, you are burning gas inside of a turbine, and that is rotating the blades. And then that exhaust heat, because once it's expanded through, there's still a lot of heat there. Instead of just dumping that to atmosphere, you run that through a steam generator where you're capturing some of that additional heat. And then that heat is extracted and it's going to steam. You can run the steam turbine at much lower temperatures than the gas turbine. So now you're running that to a steam turbine, and so you're capturing more energy. And so you can get much better heat rates, much more effective use, pushing 60-something% efficiency of the fuel when you have a combined cycle. Where for a simple cycle, and a lot of this has to do with Carnot efficiencies with temperature, but you might get 30%, maybe 35% efficient on a simple cycle. So again, simple cycle, not a lot of equipment. You got a gas turbine connected to a generator with some protection and some controls. So very low fixed costs. My variable costs are very high. So the slope of my line is much higher, and it results in that it gets to an equilibrium point where they crisscross, and that's at 876 hours. And anything after 876 hours, this facility doesn't run. So I need $114 per kilowatt year to make this plant make enough money to do that. So one of the things that when we talk about duration curves is it's a little bit of a challenge because we live, well, most of the people, all the people who live in New England, we live in a deregulated market. And so the transmission owners, so that would be Versant, that would be Central Maine Power if you're in Maine. If you go to Connecticut, Eversource in Massachusetts, Public Service New Hampshire, those are the different utilities. They're precluded by law to own any generation. So they can't actually cite or even specify the type of generation. And so the Independent System Operator of New England, ISO New England, they're the ones who sort of help with analyzing and figuring out, is the system going to be viable and make sense. But even with all that being said, the people who are proposing these generating facilities, they actually need to do their own due diligence to say, what can we sell this power at and make money? So if they're coming in as, look, we're just a peaking plant and we're only going to make money for 5 days a year, then they're designing their facility and locating it to support that. Whereas if somebody comes in and say, no, we really need to be a baseload plant, we're going to try to spend a lot of money to design a really solid plant, but we're going to be able to compete very effectively because our variable costs are going to be so low. So they would do their due diligence for that. So in a deregulated market, that takes a lot more player to get involved, because technically you could have a bunch of peakers that would go online and then they would have to run for very short periods of time, but electricity costs would be extremely high. But some people would get in the market and get in the game and say, well, we'll build other plants, an alternative plant that's going to be a much lower cost to do that. And so there'll be, that's the concept of a competitive market. It's just difficult with power plants to have the competition because it takes years to get these built. And if you're not competitive, you're designing something to last hopefully 10, perhaps 20 years, maybe even longer. The markets can change quite a bit over that period of time. So there is a different set of risks involved, but that's something that developers spend time getting into, and then hopefully you'll have an appreciation of what is going on by understanding the supply side economics. So that's all I have for today's discussion on supply side economics. I hope you found it fascinating and gives you a little bit of a perspective of how complicated this whole process of analysis is. So with that, thank you very much and have a wonderful day.